All right, maybe let's start. People will come in as they come in. So thank you again, Roman. It's a great pleasure to have you here from Tornado Cash. You're one of the co-founders, and my understanding is you are basically the chief engineer there that built the whole amazing protocol that is used by so many people. Probably one of the best CK products on mainnet right now. So without further ado, maybe I should just let you take it away, Roman. Thank you.
Yeah, but we built it based on all the research done by Zcash guys. So they are the ones that made it possible.
Yeah.
Okay, so I can say some general words about Snarks first. So they are usually used like zero knowledge proofs for two different purposes. Well, they're kind of similar, as I will explain. First is like zero knowledge part, where prover has some private information that he doesn't want to reveal to verifier. And the second application is data compression. And it's very useful for blockchains because data on blockchains is very expensive usually, especially like on blockchains like Ethereum with high gas fees for storage. And where data compression comes from is like for zero knowledge, we have some private data, put it into Snark, generate some proof, and then send the small proof to verifier. And proof size doesn't depend on amount of this like private data that we supplied. But if we want to use it for like data compression, if we want to upload something on blockchain, but we want to reduce the amount of data that needs to be uploaded, what we are doing is we're basically hiding this not very private data, but we're hiding it from blockchain basically. So the blockchain doesn't need to know the data that was used in a proof, but usually for this case, like rollups, for example, everyone else can fetch this data from somewhere. Very simple example of data compression. We can just look at the code a little bit. Tornado trees is part of Tornado Cache. It's a little bit complicated, but we don't need to look at most of the stuff. So first, I'll say a little bit of general words, like how it works. So imagine we want to upload a large array to a blockchain, and we want to be able then to check membership of certain elements in this array. The simplest way is to just upload, put all this data in Merkle tree and just upload Merkle root to the blockchain. This is, for example, how large airdrops work. There is no like zero knowledge. They just like upload Merkle root, and then whoever wants to claim their like Merkle drop of some tokens, they proves that their address exists in the Merkle tree of this airdrop. But what if we want to check if each element that is uploaded is valid? In this case, we cannot just upload Merkle root, because what if actual elements are different? So we either need to build this tree on chain and verify it, and it takes a lot of hashing and could be very expensive. And the alternative way is to build it off chain and then use zk snark to prove that it was built correctly. Tornado Cache utilizes it for something similar, but it uses like updatable tree. So what if we want to add new elements to this tree, like over and over? For example, this can be useful for rollups that have a stream of incoming transactions, and they assemble them in blocks and then publish blocks of transactions to the chain. What Tornado Cache does is a bit simpler. So it's not transactions, but just some data items. And how it's done is we have some Merkle tree of some depth. For example, in this case, I don't see the constant, but it doesn't really matter. So we have Merkle tree for example, let's imagine it's like 32 levels deep. And we can specify that it can only be updated using chunks, for example, of size, let's say 4. Like each time user uploads something, it has to have like 4 elements. In this case, we can, let me show a simple picture of Merkle. Don't pay attention to the like labels. I just pulled the first image of Merkle tree that I found. So let's imagine we have a large Merkle tree, and what we upload are subtrees of the same size. So we upload one subtree, then in the second transaction we will upload a second subtree, and then the next one. Why the size of this subtree is fixed is because when you are writing a Snark, they are not really like Turing complete. So you need to specify exact size of the computations that you need to do. So you need to specify some chunk. It's possible to do updates of arbitrary size, but in this case, like for example, when we are adding a subtree to Merkle tree, we just need to hash all the elements in the subtree and then hash only the updated like Merkle path. So we hash all these 4 elements, get this subtree root, and then do a single insertion to the tree. What we alternatively could do is insert elements one by one. For example, we can use Snark to insert, like write a special Snark that inserts one element, then insert second one, and so on. But this will take a lot more computations, a lot more hashing. So this is what Tornado Cache does in this case. And also, we want to put these new elements. So when we want to update the smart contract state, what we submit to the smart contract is previous Merkle root that we had, then updated Merkle root. Those are like our public inputs. So the smart contract will check that previous Merkle root is exactly what it has in his storage. And then also we put all the new elements in call data if we want smart contract to verify some parameters of these elements, for example. But smart contract doesn't need to put them in storage. So this is where savings come from, because call data currently is relatively cheap. It's 16 gas per non-zero byte, and there is an Ethereum proposal to make it even cheaper. And storage is 20,000 gas per 32 bytes. So it's 600. So it's like 2 orders of magnitude more expensive. So when we supply all, if we want to supply all the subtree elements to call data, if we do it as Snark public inputs, we will have to pay. If we see look at the typical Snark verifier, let me just, okay. Let me try another project. If we look at the typical Snark verifier, it accepts some Snark proof. Maybe, I'm not sure whether students already learned what it consists from, but it also accepts all the public inputs. And for each public input, it has to do one scalar addition, like elliptic curve addition, and one elliptic curve multiplication. So it's around, so this is done for each public input in the Snark. And this costs around 6,000 gas per input currently. So there is one possible optimization if we have a lot of inputs. For example, if our subtrees, I used an example of like 4 elements, but usually it's larger, like for example, 256 elements. This can get quite expensive if all of them are public inputs to the Snark. So the possible optimization that is usually done in such cases is we take all the inputs that are supposed to be public and hash them. And we hash them both in the Snark and in smart contracts. So we still supply all this input as call data to smart contract, and we still supply all these inputs to our Snark, but we supply it to our Snark as private inputs. And now the only public input that our Snark has is hash of all these other inputs that are supposed to be public. Let me try to, maybe it's a little bit confusing, so let me try to show you in the code. Let's see. Okay, so we have some inputs that I discussed before, old Merkle root, new Merkle root, and this is, and leaves is the, in our example, it was like 4 leaves in a batch. And this is like sub elements. So in our case, it's not very like relevant to this lesson, but in our case, all the leaves are hashes of some 3 useful values. So we want to store some structure in the leaf, so we hash all the items in the structure and put the hash in the leaf. And basically, we take all these arguments that need to be public, roots, and these hashes, instances, and blocks. For example, path elements is like Merkle path. It doesn't need to be public, so it's not supplied to our hash. And what this circuit does is basically computes SHA-256 hash of all the elements that are supplied here. So, well, the details doesn't really matter much, but it basically puts them, beautifies all of this data, puts it sequentially, and computes a large SHA hash. And our smart contract will do the same. Somewhere in our smart contract, what we do is we have this data, it's a large bytes array, and then we put all this data supplied in our like call arguments sequentially in this like large byte array and compute SHA-256 index hash, and this will be our public input to the Snark. So using this optimization, we reduce the amount of curve multiplications and additions that need to be done in the Snark verifier. That greatly reduced cost. But we pay for this basically by having more constraints in Snark prover, because now it needs to compute SHA hash in addition to all other computations. We still pay for the call data in Solidity. So we still need to upload all this data to Solidity. And in addition, we pay for SHA-256 hash of this data, but it's much cheaper than doing curve operations. So this is pretty typical optimization that is used for Snarks with a large amount of public inputs. They all can be collapsed in a single hash, Okay, so let's go back to the tree updates. So basically we upload all these elements, upload old root and new root, and upload path where we inserted the subtree. For example, if we are inserting this subtree, it will be path to this subtree root. And smart contracts just checks that the subtrees are inserted sequentially. So first transaction has to insert the leftmost subtree and so on. And we can see it in the code. For the reference, this code is hosted in GitHub, Tornado Cache/Tornado Trees here. So everyone can, after this session, can go and take a look. I'm just looking only at the interesting parts of this repository, because it can get like quite large. So basically, we upload some proof, new root, hash of the arguments, like two roots. Path indices is basically the path to the subtree, and some data that we saw here before. So this is the array of structures that contains like 3 entries. So our leaves are constructed from this. So all the smart contract basically does is it puts all the elements in this large array to compute the hash, and also it checks, it does some validation on the leaves. For the purpose of the current lesson, it doesn't matter what exact validation, because like for different projects, for rollups, it can be different. And that's it. Then we basically check the proof. And then we have an option. We can either emit an event with all the data that was supplied here, or we can just leave it as is. Emitting events is somewhat expensive. It is around 10 times more expensive than call data. So if we take all this data that was inserted and emitted, we pay around 10 times more than we paid for call data here. But it will be easier for everyone to reconstruct, like, for example, some other user wants to rebuild the Merkle tree locally to reconstruct the state. For example, he will want to do some Merkle proofs industry, for example. If we emit this using events, the user can just ask a node, Ethereum node, for all the events, fetch them, and build the resultant Merkle tree from them. But there's also an option to save a lot of gas expenses by not emitting events, but making it much harder to reconstruct the state. It's still possible. And how it's done is the user will need to fetch all the transactions that call this method, then fetch the transaction data from blocks. So all the transaction bytes are still in Ethereum blockchain. And then decode the call data to find out what the user supplied in the arguments. So it's possible, but it takes much more work. But still, every Ethereum node is able to do it. You don't need an archival node for this, because all the, even like full Ethereum nodes, they always store all the blocks, all the block data. Okay, so does anyone have any questions so far?
Yeah, I saw a question from the chat, actually. I think Samar raised a question about why, it's actually, why do we quite commonly choose this SHA-256 rather than something he think might be more circuit-friendly hash?
Okay, I see. So the hash is pretty large, so we put a lot of data into it, and we need to compute it both on-chain and in the Snark. So if we choose some Snark-friendly hash, they're usually pretty expensive on-chain, and we will have to pay, for example, for Poseidon hash, a lot of gas to compute it. So since we want to save more like transaction costs, we have to work more on the Snark side. So SHA-256 is pretty heavy on the Snark side, and to insert subtree of 256 elements, for example, in Tornado Cash production smart contracts, it cannot be done in the browser, and it has to be done on like special machine with plenty of RAM to compute the Snark proof. And to build such a circuit, so in our case of 256 elements subtrees, it takes a few million of constraints. So to build such a Snark with Circum, at least old Circum before Rust implementation was released, it required machine with more than 100 gigabytes of RAM. But it needed to be done only once, and to generate a proof for such Snark, much less RAM is needed, around like 16 gigabytes or so. Also, previous implementation of Circumlib is not able to build such large Snarks without some tuning. So, for example, with Circum, let me see, not here. Just a second, it's probably in the Docker file. So, oh well, it's pretty little tuning. So before we had to supply a lot of additional arguments to Node.js, and also use like custom Node.js build, but now it's a little bit easier. And I think with the release of Rust-based implementation of Circum, most such problems should go away, because it's much more efficient.
And then Pran seems to have a different question about how do we manage it? Since we're not just dealing with the root of the Merkle tree, if the tree just gets larger and larger, how do we manage?
We need to specify the size of the tree before we build the circuit. So if we specify that tree has 2 to the power of 32 elements, this is the total capacity. We cannot go over it. Like this will be all we have.
Yeah, makes sense to me.
Okay, so this is mostly the principles behind uploading some data to blockchain and using Snarks to for some savings. So we have to pay fixed costs of around 300,000 gas to check the Snark proof. We need to pay for call data, but we save on all the storage needed for the elements. So for larger Merkle trees, this is profitable. So this is the way to go. And this is similar to what rollups are doing, but instead of just inserting some elements in the tree, they insert transactions that have some logic behind them. And usually they don't have this structure of like tree and subtrees, but the batch of transactions that they insert, they just pack them into a block rather than a subtree, so like single elements. And this is much less work because they don't need to address a certain transaction on chain after it was inserted. Okay, if there are no questions there, I can switch topics and talk a little bit about upgrades to Tornado Cash and how they're implemented.
Yeah, that sounds exciting to learn.
Oh, I see follow-up question.
That's right.
Tree cannot. Oh yeah, we have to redeploy because if the Merkle tree is full, the next transaction will just fail. We will be unable to insert any new elements. So we need to deploy some new smart contract. Okay, this is also like when we are using Merkle trees, they're usually like fixed capacity, but with Snarks, it's usually even more common problem that when you're writing a Snark, all the like loops, for example, always have to be like fixed size, similar to like we have like fixed chunk size and everything because of the way zero knowledge proofs work.
Actually, I have a question as well. So you said that because of the Snark proof, then we have to have like fixed size subtree update. Is there a rationale as to how often we update? Like, is it a cost thing or is it just something that is arbitrarily decided?
Usually each project decides this based on their own needs. But why we need to fix the chunk size at the beginning is because, for example, if we want to have 2 different chunk sizes, like for example, we want to be able to insert smaller chunks of 2 elements and larger chunks of 4 elements. And imagine we insert one like small chunk, and so the tree is filled here and empty, all this part is empty. And then we want to insert the larger chunk. So we either need to leave empty space there, or otherwise we cannot like insert this big one. In case of only two chunk sizes, there is one possible trick though. For example, if you want to have only two chunk sizes, it's possible to change logic so that small chunks are inserted from this side of the tree and large chunks inserted from this side of the tree. So for large chunks, there will be no like empty spaces ever before the tree becomes like full and the inserted large chunks from here meet the smaller ones.
Right. I guess my question was more on the resource side. Like, is there a reason to choose bigger bigger chunk size or smaller chunk size based on, you know, how frequent we need to update or costs or some cost that is other than gas fee?
Yeah,
business reason, I guess.
Yeah. For each insertion, you have to pay 300,000 gas for checking the snark proof anyway. So it's better to adjust the chunk size accordingly, so you don't waste too much gas for small chunks. And also, you need to take into account how quickly your data fills up. So, for example, if you choose a too large chunk, you will have to wait until it's full before you can upload it.
Right, and I guess that brings us to the question in the chat box as well. There's two kind of related questions. Let's see. So Samar asks, where is this data stored when the subtree is not completed yet?
Somewhere. Some server or user needs to generate snark proof that is then uploaded to the chain. So the participants somehow need to communicate this data. In case of Tornado Cache, it's a bit different because when user does Tornado Cache transaction, this additional data is emitted in the event and actually like saved on chain. So in case of Tornado Cache, it's already on chain. So someone just need to wait until there is enough of the data for chunk. But for most projects, this has to happen off chain somewhere. It's just another part of the protocol. They need to decide how they communicate. It could be a central server or multiple central servers or some P2P protocol. The next question is redeployment automated or we deploy manually? It just depends on the projects. However, developers decide to implement it. In case of Tornado Cache, the tree is so large that it never fills up. And so this Merkle tree smart contract is used for anonymity mining that already ended. So, and tree is not even half full. So there is enough extra capacity. And this is already like outdated. So we will not have this problem. But different developers just need to decide how they want it. Okay, so moving to the Tornado Cache Nova stuff.
I think there's one last question from Semar, if it's okay. Like he asked whether the accumulating the server that accumulated transactions, is it open source too? I would assume so, right?
In case of Tornado Cache, yes, but other protocols, it's usually open source because you need to open source the snark prover as a result of trusted setup ceremony. Otherwise, nobody will believe that snark does exactly what it should do. Maybe it proves something else. and the protocol that is used for accumulation of this data for a new batch, it also has to be open source, because otherwise how the users will communicate their new data to this server. So yeah. Okay, so a really quick reminder of how Tornado Cache, the current production version works. We call it Tornado Cache 2.0. It's pretty simple. So when users deposit some funds into Tornado Cache, they generate 2 random numbers. Then they hash them and send deposit along with the hash of nullifier and secret together. And then when when users deposit, the smart contract will take this hash and add it to the Merkle tree that is stored on chain and is built on chain. So when user wants to withdraw, what user proves is there is public input of the Merkle root used that contains the user's node. And this Merkle root doesn't necessarily need to be the latest one. So the smart contracts stores like 100 latest Merkle roots to prevent race conditions. For example, when you generate proof that you want to withdraw some node and then someone does a new deposit, Merkle root is changed. So yours is not the last one, but it's not a problem, because if your node was in like Merkle root 10 blocks ago, it's for sure is still in the new Merkle root, right? So because you can't remove the nodes from Merkle tree. So the user submits this Merkle root, his secret and nullifier, these 2 random numbers that he generated, and Merkle path to the hash in the smart contract Merkle tree. So what smart contract does is, or rather what zero knowledge proof does, it takes these 2 random numbers and computes 2 hashes. First is commitment. It's nullifier plus secret, hash of nullifier plus secret, this one. And also commutes the second hash from nullifier only. So we have this one and this one. This is called commitment and nullifier hash. The Snark checks that commitment is present in the Merkle root on the smart contract, and it also just publishes hash of this nullifier as a public input. And note this, those 2 hashes for external observer that doesn't know the secret number, they seem like completely 2 different random numbers. So from this one, from nullifier hash, he cannot guess commitment and vice versa. So what smart contract does is it checks that Merkle root is one of the last 100 Merkle roots, and that it hasn't seen nullifier hash before. So if user tries to withdraw the same node second time, the nullifier will be the same. So the contract will detect that it is a double spend. But if the contract hasn't seen this nullifier hash before, that means that this user tries to withdraw this node for the first time. So it gives user the money. So this is basically all the logic, and this is just like Merkle tree, like a regular Merkle tree circuit. Okay, so now Tornado Cash know how we can upgrade this construction. People that are familiar with Zcash probably will like recognize the sublink construction. So instead of just storing two numbers in the commitment, so commitment is this hash that is inserted to the Merkle tree. We now store three different numbers. First is amount. Then we also store like public key of owner of this output, and then some random number. It was called secret in the Tornado Cash implementation, but it's more commonly is called like usually it's called blinding in cryptography. So here we used more correct naming. So now commitment is hash of those three numbers, and nullifier is hash. We could just do hash of this thing. So this one is added to add ability of like viewing keys, so to be able to generate like compliance report. But to simplify, we can just exclude it and say that nullifier is we take this commitment and add like secret Merkle path to it and get this new nullifier. So now we have Merkle tree. So we do deposit in a similar way, but this time when user does a deposit, he also needs to generate snark proof. So now, since we store this structure as a node in Merkle tree, we now, and it contains the amount of funds that user has. It's possible, for example, first of all, to do transactions to some other users to their public key. So user can give you a public key and you can do a transaction. And also, since we have an amount, we can do like splits and joins and like regular UTXO model stuff similar to Bitcoin. So what transaction is on a high level is we take two nodes from the Merkle tree. So we take two leaves that are not spent yet, mark them as spent, and then generate two new leaves that are like outputs of the transaction. So we take two inputs of this form and generate two outputs of this form and insert them in the Merkle tree. So this is like generic join split transaction that has two inputs and two outputs. And what our circuit has to check. So it's a little larger than in previous Tornado Cash implementation, but it's still somewhat simple. First of all, we need to check that sum of amounts of public inputs equals to the amounts of public outputs. So no money were generated. We also need to check that each of those amounts is larger than 0. So no negative amounts are present, because otherwise we have overflows and stuff like this. Also, we to make it easier to make deposits and withdrawals, we introduce some other like external amounts that comes from the smart contracts, and like it's a public input, and smart contract will check. So it can be positive and negative, and in case of like positive one, it means that user deposits some funds. So the smart contract. So let's say, for example, this is like 1 Ether. And when the transaction is like this is done, the smart contract will check that its payable transaction function actually received this 1 Ether. If this is like negative 1 Ether, it means that smart contract has to pay 1 Ether to some output address as a result of this transaction. So what we check is actually that sum of input amounts plus this like public amount equals sum of output amount. And this is where it is checked. What else do we have to check? It's just regular conditions. We need to compute commitment and nullifier for the inputs and outputs. So for each input, we compute that we compute commitment, this one, and nullifier. We check that commitment is present in Merkle tree, so it's actually live in the actual Merkle tree in the contract. We also check that it is signed correctly, so with some private key. So our UTXO contains public key, and we need just some proof that whoever wants to spend it owns the private key to this public one. Okay, and in case the amount is 0 here, we don't actually need to check that it is a real one. So we have this condition that we check a Merkle root only if the amount is non-zero. This is needed in case if we want to deposit, we don't own any inputs. So we generate 2 random inputs with 0 amount. So this is needed in case we don't need 2 inputs. Okay, so we also emit the nullifiers. Like for inputs, we check that inputs are in the tree and then publish their nullifiers so that they cannot be spent a second time. For outputs, it's a bit simpler. We just need to publish their commitments. So the commitments should be inserted in the Merkle tree. And then we just check that amount of outputs is positive. So it's 248 bits and not more. The last check that we need to do is that the nullifiers in the inputs are not the same, that we didn't submit the same input 2 times in this transaction. And this is basically it. So if we can have 2 arbitrary inputs with arbitrary amounts and 2 outputs, what we can do is we can do deposits, we can do withdrawals, we can do transfers to other person, and also we can transfer not full amount, but half or whatever, and transfer the change, like leftovers from inputs to ourselves back. So it's a generic, you take some models that allows like shielded transactions and any amounts. For example, for Tornado version 2 that is currently in production, the amounts has to be fixed, like 1 Ether, 10 Ether, and 100, because if we allow like any amounts and someone deposits like 0.13 Ether and then withdraws the same amount, it's kind of loses privacy. But in case of Tornado Cash Nova, if you deposit, for example, 3 Ether, you could, for example, split it into 2 different amounts now and withdraw, for example, only half Ether. So the amount that is in the deposit is not connected to not linked to the amount that is in withdrawal. So any questions how it works? Oh, this is to the last one. I'm not sure that this will, like, is there a way to pass entire tree in circum as an input? I'm not sure this will make sense. Like, why do we need Snark for this? But it's possible. Live demo. Yeah, okay. I can do a live demo. If I deposit 3 Ether and withdraw 0.5. So when I deposit, what happens? I generate a transaction that has 2 inputs with amount of 0, external, like, public amount of 3 Ether, and 2 outputs. First output is 0, and the second output is 3 Ether. So I basically do a deposit and shield my funds. The second transaction I do has first this, like, shielded input of 3 Ether that is not public now because all people see is that some input from Merkle tree was spent, but they don't know which one. And there's a public output of minus 0.5 Ether. So this is what contract will send to my withdraw address. And then there's a single output of 2.5 Ether that is also shielded and belongs to me. So I have input of 3 ETH and output 0.5 to public plus 2.5 ETH to another, like, I generate another output that still belongs to me. Are there any legal implications? As long as we just write the source code and do a research, I don't think there could be implications because it's publishing source code is basically like free speech. But we don't deploy contracts and we don't run any servers. So when we write some code, we can publish it to IPFS, and someone, some volunteers from community can deploy the actual smart contracts. And as for hosting, Tornado Cash is hosted on Ethereum as a smart contracts, and static frontend is hosted on IPFS by other people also. So the way you access Tornado Cash is usually you write cache.eth/ if you have MetaMask, or use .link or .limo or whatever other system that allows access to ETH domains. And then it just resolves, and you can see the, like, hosted Tornado Cash. We can also do some demo. I can let me stop sharing for a little bit. I'll check that my MetaMask doesn't show any private info. Just 1 second, it's a little logging. Okay. So this is my public address. I log in using MetaMask, sign the message. It is used to derive my key pair. And then I can do a deposit. Gas price are, switch. Oh, I had another account logged in. Oh, I even have some balance already. Okay, so we can, for example, add some more funds to our address. So let's add 0.2 Ether to our address. So this will generate a transaction that has this as an input so that we don't multiply our unspent inputs. So the less we have, the better. So we don't have like fragmentation. It's just for housekeeping. And it will generate proof, but it will take a little bit of time because it will need, okay. Well, gas prices are pretty high. Well, let's do it anyway. It will need 20 confirmation because in addition to what I already described, we use layer 2. So when we send the transaction from mainnet, it is actually sent to a bridge to XDAI. It waits for 20 confirmation and then deposits on Tornado Cash Nova instance on XDAI blockchain. When we do shielded transactions that have no external Ether, so there are no deposits and no withdrawals, just transfers to another address within shielded pool. This kind of transaction is done entirely on layer 2, so they are very cheap. And when we withdraw, the bridge will send the withdrawn funds back to the mainnet to our specified address. So the user doesn't need to interact with layer 2 directly. So you don't ever need to change like Ethereum network and stuff. But it provides these cheap transactions under the hood automatically. The proof generation happens entirely in browser. So Tornado Cash circuits are pretty small, around 30,000 constraints. So it takes around 5 to 10 seconds to generate a proof using WebAssembly in browser. Okay, so we will come back to this in the end, maybe to see that it worked. And I can also quickly open the incognito tab and explore a little bit more what can I do, just explain. So the fund tab is used to send mainnet Ether to your account. Transfer is used to do shielded transfers to other users that are also using Tornado Cash Nova. And it uses regular Ethereum addresses, but the user has to be registered. Registration happens automatically when you do a deposit, or if you don't want to deposit any funds, but still want other users to be able to send them to you, you will, after you connect MetaMask, you will have like create account button here. It will send a cheap transaction that will just register you in Tornado Cash Nova pool. And then you can withdraw some amounts. You can withdraw any amount you want, but the UI will recommend you to withdraw some typical amounts so you better blend with the crowd. This is to prevent users from, so even though custom amounts are available here, if you deposit like 1.35 Ether and then withdraw exactly 1.35 Ether, you still will lose a lot of privacy. So if you use custom amounts for deposits and withdrawals, they have to be different. You need to split the withdrawal in multiple parts, for example. So they shouldn't correlate. This is why for new users, we just recommend to use standard amounts. And advanced users that know what they are doing can enter any amount. This can be useful, for example, if you keep some of your funds in Tornado Cash Nova and want to pay someone on mainnet. You can just enter amount. For example, I want to pay someone 0.12 Ether, enter their Ethereum address here, and then just send it, and it will appear on mainnet on their address. What do you mean? Let's start with that. Okay, so when proof generation happens in the browser, is there a script embedded on website, or does info get sent over to some server? Yeah, so there is proof generation WebAssembly. It's a static WASM file that is embedded in this static UI. There is also transaction data that gets fetched from your Ethereum node or Infura or whatever Ethereum node you are using. So it downloads all the events that happened on the smart contract, builds the Merkle tree from them, and uses it as data to generate. And then it sends the generated transaction to a relayer. So this is the same relayer system as in Tornado Cash version 2. So you don't have any Ether to pay for gas, and you want to remain anonymous. So you send the transaction data to relayer, they submit it for you, and take some small fee from this transaction. How does anonymity set interact with Tornado Cash Nova? Yeah, Tornado Cash Nova anonymity set is the sum of all transactions that happen on it. It's separate from the previous version of Tornado Cash. So it's a completely like separate project because we cannot change previous Tornado Cash contracts. We can only like write new ones, and some users can decide to use them over it. Same situation as with Uniswap version 2 and version 3. Okay, so our deposit went through and the amount is updated. So this worked. What if I send transaction to L2 and withdraw it again? If you send shielded transaction on layer 2, like to another user, both your sender, recipient, and amount you send are shielded. So the only information that is known to the public is that some transaction happened, but not much else. When you do a withdrawal, your inputs are hidden. So how much money you had in your balance and your sender address, but all the outputs for withdrawal, they're obviously public because you withdraw to mainnet. So the amount and the wallet it went to is visible on Etherscan. Any more questions?
I want to follow up on maybe this is really great. It's really very helpful and take us through. But it's a general conceptual question. I think someone asked earlier about the legal issue. I just wonder, have you been contacted by FBI or like major law enforcement people in trying to get you to help? Because I think that sometimes these rug pulls and whatever hacks, when they have gotten their money not so legally, quite often they would use a protocol like a mixer, like Tornado Cash, to try to wipe clean their traces. But did you sometimes get approached by law enforcement and try to help them to recover the identity of those people?
This is pretty risky topic because even if we want to help, first of all, there is not much we can do because we don't even host the UI. So if the law enforcement wants to know the like IP addresses of users, they have to go to Cloudflare or whoever like gateway user used, or maybe they used like command line tool directly. So we don't have any more info than any other average user on the internet. So they better off trying to ask other projects like Infura, for example. And second is it's pretty easy, like when talking about such risky topics, it's pretty easy to like say something and like hurt ourselves in legal sense. So like when you are talking to the police, even if you want to be helpful, not just like Tornado Cash, but as a general rule, like when you're talking to the police, the first advice is like talk through a lawyer, right? So it's hard to be helpful even if we want to.
And I really like the idea that basically it's all decentralized, the code are up there. So there's also no way that they can try to shut you down or to force you to help with them in a way, right?
Yeah, we don't have a shutdown button, so we don't have more access to Tornado Cash than like other users.
That also got me curious a bit about, can you tell us a bit about how the business model works? So how do you guys profit directly from this?
We cannot profit directly from this, first of all, because we like didn't deploy anything. And we don't, like Tornado Cash doesn't take any like protocol fees. And even if it did, we cannot route, like we cannot take this fee. So even if Tornado Cash did take some fees, it would direct it to a DAO, and then DAO will decide. And for the first year, all Tornado Cash team tokens were locked in the vesting. So we didn't even have a vote in our own DAO. So it's completely like decentralized and governed by you. So even if we had idea to submit some proposal, the community had to search for someone that has more than 1,000 Torn, because DAO has like this threshold to submit the proposal. So people had to find someone who has enough.
That's so amazing. Maybe I should open it to the floor again. So there seems to be another question from Semar.
How employment process works. We have some our own funds from like previous business as auditors, and we developed this public good. And in addition, the team got some Torn tokens. They are mostly used for governance, but they can still have some like value or whatever. So we have some incentive to make sure that Tornado Cash succeeds. So we do whatever we can, but everyone else can like do the same, like buy enough tokens to be incentivized and then work and develop something useful, or ask for a grant from Tornado Cash DAO, and they probably just grant it to someone if it's a useful enough idea. For example, we had a team that did research on de-anonymization of Tornado Cash users, and they developed a tool where user can enter the address and see whether it has compromised privacy, whether the user did any mistake when he used the project.
And may I? That's a new question from Print. So.
What are new things in store for Tornado Cash? For the construction that I described here, we added the amount field to the UTXO structure, but for example, we can add another interesting field, asset ID, and this will allow it to support any ERC20 or NFT tokens. So for ERC20, it will be hash of address of ERC, and for NFTs, it would be hash of address plus token ID. So this will be unique for ERC20 contract, and this will be unique for each NFT. In case of NFT, the amount will be one way. So it's easy to add, for example, support for ERC20 NFTs. We also figured out how to make easy anonymity mining without all these extra steps of claiming, withdrawing, and tornado trees. Because first we thought it's impossible at all. Then we found a way, but it was complicated. So the problem is, compared to other farming, Tornado Cash anonymity mining had to preserve privacy. So it shouldn't be, if the reward for each node is public, from the size of this reward, it's possible to calculate how much the node spent in the pool. It will compromise the privacy. So we had to do anonymity mining, but that doesn't compromise the privacy. Now we figured out how to make it easy. So the Torn will be no more like anonymity points and this swaps and like market maker stuff we had before. Just the users will get Torn directly.
Yeah, the NFT use case is interesting. So Samar has a follow-up to why would you pass an NFT through a mixer? So is the idea that so that you don't, people cannot trace who owned the NFT then?
Yeah, so while NFT is in the pool, you can transfer it to other user and it will not be visible where you transfer it. Once you withdraw it, of course, it keeps, it will still be public. So the NFT is only private while it stays in the pool. But for example, if pool supports atomic swaps, it will be possible to sell this NFT while staying in the shielded pool. So this becomes more interesting.
And if I may have one last question too. You mentioned that basically right now the default is to use the XDAI layer to basically bridges to XDAI using, is it called the Omni bridge?
Yeah. Yes.
So basically, does the bridge mostly cost the gas fee? Does it cost quite a bit when it comes back from XDAI back to ETH?
It's free. XDAI sponsors the withdrawals. But there is a minimum amount of 0.05 ETH. So you can withdraw less than this because they have to pay for transactions and makes no sense to withdraw so little. But 0.1 ETH will be free.
Yeah, I'm not so familiar with XDAI because this sounds like a lot better than some other bridges.
It's still a side chain. We are waiting until layer 2s will catch up because, for example, currently in layer 2s, you have to wait a week before you can withdraw your funds. And this is really, really bad user experience, but they have some ways to fix this. So I expect in a few months, they should catch up.
All right. So is anyone want to have any last words? If not, I think we should all really thank Roman. This is really amazing that you managed to take us through so much of this really technical stuff so nicely and in a very useful way. So okay, thank you so much.
Yeah. Thank you for having me.
Yeah, thank you. So we might I shared your Twitter handle because someone asked for it. Hopefully more people will follow your work from there.
Okay.
Thank you. Thank you so much.